Welcome to graph theory. This is the first part of a two-part set of lessons on classification of graphs. For our classification of graphs, we're only going to talk about simple graphs. Those are graphs that have no loops, in other words, no edge going from a vertex back to itself, and also having no multiple links between two vertices. The first type of graph we're going to look at is an irregular graph. That's one in which each vertex is of a different degree from all other vertices in the graph. The set of irregular graphs is empty, and we're going to prove that in the next theorem. So we have our theorem here. There are no irregular graphs of order 2 or more. We prove this by contradiction. Assume there is an irregular graph of order n greater than or equal to 2. This means that each vertex is of different degree, so each vertex has a different number of edges to the other vertices. Thus, the only possible degrees for a vertex in a graph of order n are 0, 1, 2, up to n minus 1. So for G to be irregular, there must be exactly one vertex of each of these degrees, from 0 to n minus 1. However, the vertex of degree n minus 1 must be adjacent to all the other vertices, including the vertex of degree 0, which by definition is adjacent to no other vertex. Thus, we have a contradiction, and our initial assumption must be false. We can apply our previous theorem to what's known as the parity puzzle in graph theory. So we have n people at a party. I've drawn it here for 5, but it holds in general, where for each 2 people, they are either friends or not friends. Let the people be vertices in a graph. Further, let there be an edge between 2 people who are friends and no edge when 2 people are not friends. By theorem 1, there are at least 2 people at the party who have the same number of friends. And I just have one example to show that that must be the case. So we have 5 people here. So for example, this woman is friends with this lady here. She's friends with this young woman here, as well as this man here. So she has 3 friends. This lady has 3 friends. She has 3 friends. So already we've seen that we have multiple people with the same number of friends, or in other words, multiple vertices on the graph that have the same degree. In fact, this man here has also 3 friends. Only this one here, this gentleman here, has some different number of friends than the other 4. You can play around with it, but by either adding or subtracting edges, but you'll not be able to get this into a state where each person has a different number of friends, and we've proven that in our theorem number 1. And by the way, I'm numbering the theorems here consecutively so we can refer back to them. We've seen that there aren't any graphs that are irregular, but there are graphs that are what's called almost irregular. And the definition there is a graph that has exactly one pair of vertices of the same degree. And we have 2 examples here, graph G and graph H. In graph G, A and B have degree 2, and the other vertices are of degree 3 and 1. And in graph H, A and B are of degree 1, and the other vertices are of degree 0 and 2. In general, we have this theorem here. For n greater than or equal to 2, there are exactly 2 almost irregular graphs of order n. And these graphs are complements of each other. So I need to explain what complements mean, and I'll do that in the case for n equals 4. A complement of G is a graph that has an edge between vertices that are not connected in G. So we don't have anything between A and D and B and D, but we do in graph H. And where any adjacent points in G, so A and B, B and C, those edges are removed, and vice versa. So we have no edge between, for example, A and B, or A and C, or B and C, and that's all added in its complement. So when you put these two together, you get a fully connected graph. And what this theorem is saying is that for any n, any graph of order n, so n vertices, there's exactly two irregular graphs, and those graphs are complements of each other. And then we sort of have this addition to the theorem that says that the degrees of the vertices in for the irregular graphs of a graph of order n is 0, 1, 2, up to n minus 1, with exactly one value missing. And we can see that here. For graph G, the values of the degrees are 1, 2, and 3. And so 0 is missing. There's no vertex of degree 0 in this case. And then for graph H, the degrees are 0, 1, and 2, and there's no vertex of degree 3 in this case here. We have another property of graphs on this slide. For every given set of positive integers whose largest member is n, there is a graph of order n plus 1, the degrees of whose vertices are precisely these integers. The possible graphs for the case of n equals 4 are shown in the next slide. That'll kind of give you a better feel for what I'm saying here. The general result is captured in the following theorem. Proof is omitted. So for every set S out of the integers from 1 to n, there exists a graph G of order n plus 1 such that the degrees of the vertices of G exactly comprise the set S. Keep in mind that the set S must have n as an element, right? Because we said the largest element is n, so by definition that needs to be the case. And by the definition of a set, S does not have any repeated elements. However, as can be seen when I show you in the next slide, it is possible to have repeats in terms of the number of vertices that have a given degree. Okay, so this is a little bit much to take in, but hopefully the example will help visualize what's being said here. This is an illustration of our theorem. In this case here we have the set S is a subset of the integers from 1 to 4, so 1, 2, 3, and 4. And what the theorem is saying is you can pick any subset from 1, 2, 3, and 4. I show 8 different possibilities here. And there is a graph of order n plus 1 that has vertices of that degree. So here we have 4. So we're just taking a subset, the element 4 from this to be our set S. And you notice every vertex here has degree 4. So that's what I meant by repeats. You have more than one of the same degree, but that still satisfies the theorem. There's another subset from the set 1, 2, 3, 4, just 3 and 4. And there we have 3, 3, 3, 3. So these 4 have order 3, and then this vertex at the top has order 4. Let's look at another example. Let's say we have 2, 4. And so this has order 2, this has degree 2, this has degree 2, degree 2, degree 2, and then this one at the top has degree 4. If we take 1 and 4, you can see here these will have degree 1, this has degree 4. So I'm not being exhaustive. There's 16, I guess, possibilities here. Or maybe 15, because you have to pick at least one value. And here you have 2, 3, and 4. So you have 2. These both vertices have degree 2. These two have degree 3. And this has degree 4. Okay, so you may want to try some of the other ones I didn't do, just to convince yourself that no matter what subset of from 1, 2, 3, and 4 that you pick, you can find a graph of order 5 that has vertices of those degrees and only those degrees. But again, you can have repeats, and you see that almost all these have repeats, but that doesn't violate the theorem. That's just a consequence of how these are being constructed. So we talked a little bit about irregular graphs, and we saw that there weren't any of them, but there were almost irregular graphs. So you may be wondering, well, what's a regular graph? I want to talk about that on this slide. A graph G is classified as regular if all its vertices are of the same degree. If the common degree is R, then G is said to be R regular. If G is an R regular graph of order n, then the following inequality must hold. R is greater than 0 and less than or equal to n minus 1. Hopefully that's fairly obvious, because you can only you can't have less than 0 degrees for a vertex, and you can't have n, because each vertex can at most have be adjacent to n minus 1 other vertices. So that's why R would have to be between 0 and n minus 1. A zero regular graph of order n is simply a set of vertices with no edges. So it's just n dots, basically, in our diagrams. Some types of regular graphs arise frequently and are given specific names, as noted below. The graph of order n, where all possible edges are included, is called a complete graph of order n, denoted by k sub n. K sub n is an n minus 1 regular graph, and I have a few examples here. So we have k4, so it's basically 4 vertices where you have all possible adjacencies between any 2 of the vertices. And then this is 5. It's kind of a pretty star diagram in the middle here. These crossing points are not vertices. That's just the way you have to draw it. In fact, for K5 and higher, we'll get to this later, but for K5 and higher, there's no way of drawing this in the plane if you don't want to have the edges crisscrossing. In K4, we can avoid crisscrossing. We could have taken this line out, and I can just draw it here. If I remove that one line I just pointed to and then did this, and again removing this here, then you wouldn't have any of the lines crisscrossing. But once you get beyond K4, you can't do that. You have to go out of the plane if you want to avoid having lines crossing. But again, we'll get to that in more detail later on. On this slide, I'm showing another type of regular graph. The graph of order n, in which every vertex has degree 2 and the vertices form a single cycle, is called a cyclic graph, and it's denoted C sub n. And I have some examples here: C4, C5, C7. So it's pretty simple. You just connect the dots in a cycle. And you notice you have degree 2 for each one of the vertices. Okay, so that's another example of a regular, or a type of regular graph. On this slide and the following slides, I'm going to talk about a construction proof where we can build a regular graph of any degree that we want, except for one exception, which I'll mention here at the top, by the handshaking lemma, which I've copied here for your reference, but we did talk about this in the previous lesson. By the handshaking lemma, no graph can contain an odd number of odd vertices. Thus, there are no R regular graphs of order n where both R and n are odd numbers. So other than this exception, we can always create an R regular graph of order n, and that's what this theorem says here. For integers R and n, not both odd, R between 0 and n minus 1, there exists an R regular graph of order n. And the way we do that is we start with the cyclic graph C sub n, and that gives us a two regular graph of order n. And then we look at two different cases. One when r is even, which I'll do on this slide, and another case where r is odd. So if r is even, basically we split it in half. We can write r as 2k, and then we do k minus one additional edges, say from v1 in the clockwise direction, and then k minus 1 additional edges from v1 in the counterclockwise direction. And so that gives us 2 times k minus 1, which is 2k minus 2, since we define r to be 2k, which is r minus 2. And then we already had 2 edges for the v1, for example. So that would make us r v1 of degree r, and we would do that the same for all the other vertices, and then we would get an r regular graph of order n. I'll show you a specific construction for n equals 8 and r equals 4 on the next slide. On this slide I have the example n equals 8, r equals 4. We start with C sub 8, the cyclic graph of order 8, which is in black here. And then the theorem tells us that we draw additional edges to the nearest vertices other than the 2 that are already drawn. And we go in the clockwise and then the counterclockwise. So we only need to do 1 in the clockwise direction and 1 additional in the counterclockwise. And we get 4 edges coming out of V1. In other words, it's of degree 4. Then we go to V2 and we do the same thing, and V3 and so forth all the way around. And then we have, as you can see, a graph of order 8, and it's 4 regular since each vertex is of degree 4. If we wanted to make this 6 regular, then we can add some edges using the same technique, and I can show you that. So let's start with V1. So we already have something to V2 and V3. We would add an edge to V4. Then we have another edge to V6. I won't do it all the way around, but then you would do the same thing for V2. You would go to V7 and V5 and so forth, and then you would, once you circle around, then you would have all the vertices of degree 6. So you would have a 6 regular graph in that case. When r is odd, in other words, we can write r as 2k plus 1 for some positive integer k. Further, we know that n must be even given the exception mentioned previously. We can't have both r and n odd. So n is even. For each vertex, v sub I, draw or add edges to r minus 3 of the nearest vertices. And the way we do that is we draw k minus 1. Let's just look at v1 here. We draw k minus 1 in the clockwise direction, and then k minus 1 more edges in the counterclockwise direction. And then we still need to add one more, and that would be to the diametrically opposed vertex, for example, from V1, so to V5. And that would give us a total of 2k plus 1 edges if we add in the 2 that are already there from our C sub n. Okay, so I'll show you an example of a few more examples actually of how this works, how the construction works. So let's look at a few examples. We already did this one, n equals 8, r equals 4. I copied it here again because I'm going to do n equals 8, r equals 5. And basically you do n equals 8, r equals 4 first. And then the part about the diametrically opposed vertices being connected is what I've added here. You notice this had 4, for example, this vertex. Then since n is even, there's a diametrically opposed vertex here, and we added an edge between these two. And we go around and we do it for each one. And since we have an even number, everything balances out, even number of vertices, I mean, and everything balances out. And so you get 5, 5, 5, 5, and so on. So that's how you do it, where you have an odd number for your R. So this is a graph of order 8 that's 5 regular. This is a graph of order 8 which is 4 regular. Okay, we have one more example. In this case, n is odd and r is even, 7 and 4. So we have 7 vertices, and we do the technique from case 1. So we start here, for example, and we draw 2 additional edges out of this vertex, and then we go to the next one, and so forth all the way around. And then we see that each vertex is of degree 4, so we have a 4 regular graph of order 7 in this case. Okay, so that was the first half of my lecture on classification of regular graphs, simple regular graphs, and then I have one more lesson on that to follow, and then I have a few more lessons on other topics from graph theory after that. And finally, the last lesson is a set of exercises that make use of some of the theory and ideas that I've discussed in the previous lessons.